There we go. Can you see my slides?
Yeah, it's clear and visible.
Great. Please, I'm sorry that I got the date wrong on the slides, but I'll correct that. Okay, so my point of departure is that there's a parallel between legal texts and programs. And in particular, the methods used to interpret them may have more in common that we can say something interesting about. So judges frequently interpret legal texts by having to decide, for example, whether vehicles in a law against vehicles in the park includes electric scooters. It's an interpretive question about the scope and the meaning of a law. There are also circumstances under which judges have to interpret software. So, taking a classic example, United States versus Morris, the internet worm case, whether that was prohibited under the Computer Fraud and Abuse Act hinged, for example, on whether his use of bugs in SendMail was part of the intended use of those programs. So this raises a question of what the legal meaning of a program is. Now, under ordinary circumstances, we think of legal texts as being addressed to people, particularly judges, and their meaning is based in interpretation of natural language. What do they mean to people? And programs are addressed to computers. They are instructions for a computer to carry out various commands, and the computer does something in response. And so it seems that their meaning, their semantics, is based on their functional effects on the computer. So this gives us a first interpretive strategy for thinking about what a program means. I call this naive functional meaning, and it just says, for judges, for legal purposes, a program's meaning is what it causes a computer to do. This is conceptually simple because it means that you link a semantic concept, the meaning of the program, to its functional effects in terms of how it causes the computer to change state. It's also operationally very simple for a judge or other legal interpreter to carry out because you have a very clear decision procedure for deciding what the program means. You just run it. You observe the results of the execution, and that is the semantics of it for all legal purposes. And this leads to a really interesting comparison because natural language is notoriously vague and ambiguous. That vehicles in the park raises questions about the definition of vehicles, a term that has potentially overlapping meanings, may differ from one community to another, and this introduces lots of well-known problems in legal interpretation about trying to fix the meaning of the terms used in a statute and to pin down how to apply it to change circumstances. But it's comparatively very easy to observe a computation. Again, you just run the computer and find out and watch the results. And people will look at the computer and they can generally agree on what it did. So this seems to offer and hold up programs as a comparatively clear contrast to the language in which statutes and other legal texts are written. So this is behind some of the drive towards coding law. We can replace ambiguous natural language with clearer computer programs, and that this will clarify and clean up legal interpretation. There is, however, a problem, or several problems, with this approach. And so I want to, in the process of refining and dealing with those objections, show how these interpretive strategies wind up starting to need to borrow from the same kinds of things that make natural language interpretation of legal texts potentially contestable and ambiguous. So the first objection is that real-world computations don't always succeed. Programs sometimes have problems. The actual physical computer on which a program is run could fail. It might be unplugged in the middle of it. Bits of memory could be hit by cosmic rays. The hardware could malfunction. It could produce potentially unpredictable results. Naive functional meaning would just say that the failure mode is the program's meaning. It does what the computer did, even if that was blatantly in some sense wrong, even if the hardware behaved in some crazy, unspecified way. naive functional learning would still treat that as the meaning of the program. And if you think about the circumstances in which we ask what a program means for legal purposes, take a smart contract or take a program that secures access to a computer, this is going to be clearly wrong. If the ATM debits your account and then crashes before emitting cash, the bank still owes you the money. It's not a defense to say, well, the meaning of the ATM software was what it did, and it didn't give you money, so that's correct. You're still entitled to that money. So the response here from the programming language community, and this will not be novel, is that we have a distinction between correct and incorrect executions of a program. That we abstract away from any particular computer to the meaning that the program should have when executed by any correctly functioning computer. And how do we specify that meaning? Well, we have a definition of a programming language, the language in which this program is written, and we say that a program is correctly executed when the actual computer produces an output in accordance with that definition. And there are a variety of techniques used to pin down meaning in this way. You can write a specification for the language that describes what it does using natural language, but hopefully precisely enough that people will agree on which implementations are correct and which aren't. You could give formal mathematical semantics, which provide hopefully a grounding in a set of formalisms that people agree on are precise. So when we think about programming language semantics, we're usually discussing something along these lines, in which the specific expressions in the programming language have particular meanings. We can compose them together to generate the formal mathematical meaning of a program. You could also do it by example. Produce a piece of software and say, this piece of software is the reference interpreter, and whatever this piece of software does is by definition correct. Or you could do it inductively and say, here are test cases. Your implementation should conform to these test cases, and based upon those, you can inductively infer what it should do on other inputs besides the ones that are specified in the list of test cases. What all of these have in common is they derive the meanings of individual programs from a definition of a language that can encode multiple programs. So this leads to a second and more sophisticated interpretive strategy. It's based upon functional meaning in the naive sense I discussed before, but it's a more sophisticated way of extracting meaning from effects. So here, a program means the effects it would have on a computer that correctly implements the language in which the program is written. This is based upon the abstract definition of the language and of programs written in it, rather than on concrete executions on specific computers. And this solves the problem of hardware failures. It deals with the problem in which the cosmic ray flips bits in memory. It says that those were incorrect. The meaning is what it means according to the abstract definition of the language. We are now thinking about a program as a text, something that is a sequence of characters written in some language, rather than as purely a bunch of concrete hardware ones and zeros written on a specific device. And this works, but it comes at a certain cost. And this cost is that it's now dependent on social agreement among people. We have to agree on what the language semantics are in order to agree that a program conforms to those semantics. If you look back at the list of ways we specify meaning, reference implementations and natural language definitions and formal mathematical semantics, all of those are documents provided by people. We have to agree that this document defines the meaning of a program written in this language. We have to agree that this thing in front of us is a program in this language. And that agreement can change or break down. One way that it changes is when the definition of a language changes. When you move from one version of Python to another, programs become valid or invalid or have their semantics change based upon language changes. And the same for any upgrade. So there are expressions that are invalid in one version of Python and valid in another. And the social convention that we are looking at a Python program has shifted underneath that program. The semantics have shifted almost invisibly. In other cases, disagreement endures. Different browsers implement the CSS language differently. If you think about the semantics of a program written in HTML and CSS in terms of what will show up on the screen, that meaning is different in different implementations of it. And so we get some of the ambiguities that we see with natural language interpretation sneaking back into programming interpretation. And the most significant gap that literal functional meaning still leaves open is the problem of buggy software. So suppose that I write a program that draws octagons, and when it's run, it draws 8-pointed stars again. I start debugging, I look at my source code, and I realize that I wrote 135 rather than 45 for the angle. I was thinking about the degree by which each corner deflects, when in fact it should have been the angle there. So I fix it, I change it to 45, I might have a new program, the new program draws an octagon, I have fixed the bug. From the point of view of naive and literal functional meaning, these two programs are different, but they're equally valid. Both of them are perfectly plausible programs. Both of them are programs that produce a certain result when run. There is no reason to prefer one of them to the other. But for me, the programmer, one of them was buggy and the other one is correct. And the audience of users, people who want to look at octagons rather than stars, one of these programs is buggy and fails to do what they want, and the other is correct and does do. So to the extent we have a distinction between buggy code and correct code, that distinction is coming from someplace outside of the definitions we have. We need a new concept of program meaning to take account of it. And so here's a third interpretive strategy. I call this ordinary functional meaning. Legal theorists who talk about statutory and contract interpretation will frequently distinguish the literal meaning of a text from its ordinary meaning. The literal meaning is a very crabbed and unnatural way of reading it. You could read a text and it refers, based on financial regulation, refers to banks. The literal meaning there might also potentially include the banks of a river rather than financial institutions. That is one plausible literal meaning of the text. But the ordinary reader, the reasonable person who is looking at this text, that reasonable reader will know that from context you're referring to financial institutions. The reasonable reader also ignores typos, obvious missing negatives. They can do a bunch of repairing automatically because they know that this text was not meant to say what it literally says. In a somewhat similar way, we could talk about ordinary functional meaning. What would a reasonable reader of this program expect it to do if it were bug-free? The reasonable reader is like a programmer who's part of the community of programmers who write code in this language to do this kind of task. And this ordinary reasonable reader may well be able to correct for things like syntax mistakes, missing tokens. They may also be able to do more complicated fixes to say, oh yeah, you have a memory overflow here, it leaks memory. But if this program actually ran for as long as it was supposed to, it would do this. And our concept of correct functioning, of a bug-free program, presumes that this distinction exists. We have a sense that this program would do this and it will do this once I fix the bugs. So here comes the punchline. Which interpretive strategy is the best? Well, they all are. They are all appropriate under different circumstances. A programmer who is engaged in debugging is actually mentally switching between the three strategies on the fly. they're holding up the idea that what the program is currently doing, its literal or naive functional meaning, is different from what I want it to do. And they're searching for the source of the problem potentially in the hardware and the specific failures of this execution environment, or a failure in their specification and coding. They're looking at the divergences between these three meanings in order to understand why the program isn't working. And similarly, judges and lawyers who are looking at computer programs and trying to figure out what their legal effects are going to need to switch between these strategies. So to go back to the Morris Internet Worm case, that's a case in which the literal functional meaning of send mail and fingerD allowed him to install his worm program by exploiting buffer overflows. The worm program was installed by doing that. But the court holds that this was a violation of the Computer Fraud and Abuse Act because these weren't the intended functions of these programs. In other words, the ordinary functional meaning of send mail and fingerD excluded the ability to install your own software on the computer by exploiting a buffer overflow. The court's holding, in essence, is that these two concepts diverge. And there are other cases, like the ATM, where those two concepts are going to diverge again. And there are also going to be situations in which the actual execution is something people should be able to depend upon. If you've got a misspelling, a typo in your robots.txt file, somebody is programming a bot to scrape web pages shouldn't have to figure out that you misspelled the word disallow. That's on you. They are entitled to rely upon the literal functional meaning of your robots.txt file in terms of what their bot can crawl. So my claim is just that in legal settings where the meaning of a program is at stake, you have to have all three of these concepts available. And indeed, if you want to think more broadly, there are going to be other kinds of meaning as well. Source code comments have no functional effect, and yet they also convey meaning to people encountering programs. So a theory of legal interpretation that needs to make sense of software is going to have a variety of different kinds of meaning because the reasons and the context that we interpret things in law are diverse and complicated and context dependent. And so my broader project here, which this is a part of, is trying to figure out how legal interpretation can learn from program interpretation and vice versa. And with that, I am happy to switch over to take questions and discussion.
Thank you a lot, James. So we have the first question from the audience.
Hi. So I'm a bit confused about how you're understanding United States versus Morris. So just for everyone, so United States versus Morris is first major case interpreting the Computer Fraud and Abuse Act, and the question there, I thought, was, well, there were two, but one, by introducing the worm, did Morris intentionally access in an unauthorized manner other accounts? And that has nothing, and whether he intended to do damage and whether that the statute requires that. None of those two questions have nothing to do with how to interpret send mail or the finger daemon, because those are Unix services. And the question is, did he, Robert Morris, intend to get unauthorized access? And that has nothing to do with how to interpret send mail or the worm. So I don't see how the question you're posing, you're trying to answer, is works in with the question that the court was wrestling in Morris. I may be confused in that question, but I'm confused.
The specific doctrinal hook is the question of authorization. In particular, I take it that he would have been authorized to use SendMail in order to deliver mail to people using the systems he was accessing. So they'd set up a program that allowed some accesses. And so the question is, was his use of this program that he was authorized to use as an outsider beyond the scope of that authorization? And that's where you get into the legal question, because merely by deploying code to the internet, you can authorize other people to use that code in some ways, but not others.
Can I just follow up? But that's a question of the security policy of whatever Berkeley and Harvard and all the other universities that the worm infiltrated. You ask, is a security policy of, let's say, Berkeley to allow Robert Morris to access, somebody else's account? And the answer is no. That has nothing to do with the meaning of SendMail. That's just, does Berkeley allow people to do that? And the answer is no. So I don't see how that has anything to do with the interpretation of SendMail.
The program, merely through functioning the way that it does, expresses security policies. Most websites have terms of service, but most people don't read them. And to the extent the terms of service say, you cannot visit this website even though it is publicly available, most courts would say that the terms of service don't control over the fact that the website is there and publicly accessible. So the mere fact that a program has certain functionality can convey permission to use it in some ways and not others. The same thing would be applied to the ATM software or to a robots.txt file.
We have one more question. Yeah.
Hi. One question, one concept that I thought was missing from a presentation is that of a specification. So something external to the software that specifies what the expectations, for instance, of society are, if you look at what standards sometimes specify. How does that fit into your framework?
That's a great question. And I would put that in the same category as source code comments, because a specification can say, for this particular program, we are expecting this kind of behavior. And so some of these can be given using very precise mathematical strategies. You can have a specification that gives in some technical detail how it should function. Other specifications are much looser and written in natural language. And yes, that is a place in which you could be relying upon these looser natural language concepts in order to try to describe what this technical artifact the program should do. And so, yeah, a fuller theory would have to describe the relationship between a program and its particular specification.
Hi there, thank you for the talk. So you talked about sort of lawyers and judges and programmers looking at the text, but most people don't experience programs through the program text, right? They use it. And often we're not allowed to even look at the text. So is there a kind of concept of ordinary interpretation of how you use the program, similar to like what an ordinary citizen believes the law to be and not what it actually is? Is that a kind of concept that's used?
Yeah. So I've described a taxonomy of functional meaning, and that should include also some notion of user meaning that's based upon the program's user interface, because that's the community that experiences it. And so that would include, things in its display and potentially text in English shown to users describing, click here to do this. And so to understand how a reasonable user of the program would understand it, you're going to have to understand both the wording in the interface and also its affordances. When you click this button, the following things happen. And that's tied to both the things it displays and to the underlying functionality. Like, I see this current project as just the one brick in building that larger theory.
Hi, James. Thank you for the paper. It's fabulous. I should say that we will be publishing this paper very soon in the Journal of Cross-Disciplinary Research in Computational Law. So look out for that in the next few weeks. My question relates to the source of the program that you're referring to. So far, I think you're focusing on the interpretation of programs by judges, commercial programs, that is. But of course, the focus, and I think you alluded to this in the talk, something that's developing and I think is very relevant to people in the room is the rules as code movement or field, which is burgeoning. And I wondered if legislation is represented in code that's potentially executable. There's a range of levels of execution, of course. I wondered there if there's a particular application of your framework of interpretation there, where the source of the code is the legislature, is the state, rather than a commercial enterprise which is developing a program, putting it into the world, and then it needs to be assessed for liability purposes. Flip it around. If the source is the state, if the source is the legislature putting out rules as code, how do your interpretative strategies figure in that scenario?
That's another great question. One of the big lessons of legal interpretation is that it's highly context dependent. The rules that judges use to interpret statutes, which are written by a legislature and intended to be binding on a bunch of people, are different than the rules they will use to interpret contracts, which are drafted by parties negotiating with each other and are meant to reflect a private understanding binding on themselves. And you can go on, like, different legal contexts generate different sources of evidence, different norms of interpretation, and different effects. And rules as code are going to have that context dependence built into them. There are also going to be problems about sources of authority. When you have a statute that has then been subsequently coded up in order to have an implementation that is meant to represent it, the relationship there is going to be different than if the legislature supplies the formal implementation itself. What do you do in a case where the legislature provides both a description of what the implementation is meant to do and an implementation, and the two diverge in some way? That's in some ways going to be like the problem of operative text that's different than what's in the preamble or the legislative history. And that interpretation is going to need some way of fitting these external constraints or pressures or descriptions to the actual functional effects of what do you do when you run this code and see what happens. And we've seen some of those divergences in disputes over buggy smart contracts. I think there's not a clear single set of rules that work all the time. I'm trying to think through what that context dependence is and what the different rules that would apply to different interpretive contexts are for those divergences.
Thank you, James. So let's thank the speaker again.